This lesson is about properties of pseudo-random noise, which is famously called PN code, which is used predominantly to achieve the spread spectrum communication. And to discuss the properties, we observe that there are two important properties that are known for PN sequences. The first one is the randomness, and the next one is unpredictability. These are the basic requirements that a PN code must satisfy for it to be able to achieve the objective of stopping jamming or interference of the transmitted signal, so to speak, enemy territory. So to start with, we say that there are three criteria that are used to validate that the sequence of random numbers, or rather the sequence of this PN code is random. The first one is called uniform distribution, in which case we say that the frequency of occurrence of zeros and ones, or the digits in the PN code, which are predominantly or always zeros and ones, they should be approximately the same. So for instance, if we have a PN code with n equals to 32, approximately the number of ones should be approximately 16, and the number of zeros should be approximately 16. Sometimes that may not always be the case. When the n is not very high, is not approaching infinity, we might realize that the number of ones may be different from the number of zeros by a difference of 1. That is the maximum number. So if we have n equals to, say, 7, so in case it is 7, an odd number, you realize that the number of zeros are going to be, say, 3, and the number of ones are going to be 4. So the maximum difference between these two is a 1. So that is the property that is known as correlation. These two properties are very related. It says that when n is approaching infinity, then the number of zeros and ones are said to be the same. But for a small number of n, the difference between the number of ones and the number of zeros is a maximum of 1. The other criteria that is used to validate that the numbers are random is that of independence, such that no one value in the sequence can be inferred from the other. When we see from 1, 0, 1, 0, we cannot expect that the other two numbers are going to be 1, 0, 1, 0. We cannot be able to predict the next bit of our PN sequence from what we have observed before. So that is another very important criteria that must be satisfied, or we use to validate that a sequence meets these two properties of PN sequence. So for instance, this is the PN sequence that we produced in the previous class or the previous video. And if you count, the number of ones are 1, 2, 8. So the number of ones in this 15, in this case n is 15, the number of ones in this case are 8, and the number of zeros are 1, 2, 3, 4, they are 7. So we can clearly see that the balance property or correlation property is satisfied, and also the one that we have mentioned of uniform distribution. When n approaches infinity, the probability of observing bit 0 is a half, and the probability of observing symbol 1 is a half. This is when n approaches infinity, but otherwise the difference between the two is always maximum of a 1. We proceed to the other property called the run property. We're talking about the properties that we use to validate that a given PN sequence meets the required two properties of randomness and unpredictability. And in this run property, we observe two items or two terms. One is the total number of runs, which you might see as describing it as TR. And the number of runs is, we are going to define it as this. The number of continuous similar digits may be 1, may be 0. So this is one continuous of 0, which has 3. The number of bits that are continuous is 1, which is appearing with only one number of bits. These are two continuous zeros, so we can call them 2. These are two continuous ones, 2, only 1, 0, only 1, 1, only 1, 0, and 4 continuous ones. So the number of runs are this: 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 runs, and therefore we can define the number of runs TR to be given by n. N is the number of bits or digits in our PN sequence plus 1 divided by 2. So the total number of runs for us to satisfy the run property, which ensures randomness and predictability of our PN sequence, requires that the total number of runs are always going to be given by this formula. And as we have seen, for n of 15, we have seen that our runs in this sequence is 8. The other property or characteristic of run property is what we call the length of each run. And the length of each run, say for instance, the length is n. This is going to be given by a formula that 1 over 2 to the power n times TR gives us number of runs of this length. So for instance, a run of length 3, n is equals to 3, we use this formula to find how many runs of rank 3 do we have. And we have seen that this is one of them. We want to confirm, we can only see one here. Let's confirm from this formula that the total number of runs of rank 3 are how many. So we say 1 divided by 2 to the power 3 times TR. TR is, we have seen it's 8, and we can clearly see this is 1 over 8 times 8. That gives us 1, and therefore we are going to have a maximum of a length of 3 is only 1. Let's do another example. Assume that now n is 2, and therefore the total number of runs of rank 2 when we can count are 1 and 2. So from that, let's confirm that we are going to get 2. So that is 1 over 2 to the power 2 times 8. This becomes 1 over 4 times 8, and this is equivalent to 2, and that confirms that the total number of runs of rank 2 is equals to 2. And finally, let's finish here. Assume we want to find out how many runs of rank 1 do we have, and we just use the same formula. Will be given by 1 over 2 to the power 1 times 8, and this means that the total number of runs of rank 1 is 8 divided by 2, that is 4. So if we count the runs of rank 1 is 1, 2, 3, 4, and therefore that satisfies the run property. So we proceeded now to look at the other property called the autocorrelation property, which again is used to validate the requirement of randomness and predictability. And we use this property to validate that if we have received a PN sequence that satisfies this property, then that sequence is random and it's predictable and it's valid. So how do we do that? We start with looking at this sequence, and there is a formula that we use to define the autocorrelation property of a digital sequence, and we say that if you remember, tau was the length of delay that we are introducing in between the current sequence and its correlated sequence. We normally use that the autocorrelation function is given by 1 over n, C of n, and this is our sequence, multiplied by C of n minus tau. So where tau is the difference or the delay that you are introducing between the current sequence and the one that you are observing or you are correlating. So tau is the difference or delay, and C is our code. So C is our code, and our code is going to be generated as follows. For when we observe, we want to find our C of n. Therefore, C of n is going to be defined as follows: that when we have a 0, we encode it with a -1, and when we have a 1, we encode it with a +1. So here we have a series of zeros and ones, but we don't want to those zeros and ones. We want to use a code or like a line code that we are defining that whenever we have a zero, we encode it with a pulse of -1, and when we have a base 1, we encode it with a positive pulse of value 1. For that reason, we can now be able to generate our code from this sequence as follows. So this code is going to come as follows, that we have seen that for anywhere we have a 0, we have a -1. So this becomes -1, -1, 1, -1, 1, 1, 1. So that is our Cn that we are going to use when we are defining or when we are evaluating the autocorrelation function. And our C of n minus tau, we can let tau be equals to 1. So how we are going to obtain tau, we are going to do cyclic shift. Whenever we have tau is 1, we just do a cyclic shift. Whatever we had here, we bring it in the beginning. So we are talking about tau is equals to 1, and therefore all these others, we do cyclic shift them by 1 bit. That causes our delay of 1. So this will become here. So we are simply doing a cyclic shift. This one comes at the beginning. That is why we have this one here. So everything else comes as you have seen. So this becomes our final C of n minus tau. And now, as you remember from our autocorrelation function, R of 1 now, because our tau is 1, is going to be given by 1 over n is 15. So we put our 15 there. Sum of Cn times C of n minus tau. So in this case, you're going to be simply doing cross multiplication of each of these pulses. Therefore, whenever we have -1 times 1, that equals to -1 plus, of course, this is summation. So when we change this symbol, it means that we are going to be adding the products of these two. Remember the formula, we have defined it as 1 over n, sum of C of n minus tau. This is equals to autocorrelation function of tau being the delay. So we have evaluated this code, and the code of 1 delay tau of the tau. Therefore, we multiply these two. This is what simply this means, that you're multiplying this code with this code. So whenever we have -1 times 1 becomes -1 plus -1 times -1 becomes +1. -1 times -1 becomes +1. So when you complete this summation, you are going to observe that the final result becomes -1 all over 15. That is for when you have a delay of 1. There is one that we have not done. When we have a delay of 0, the autocorrelation function will actually mean that our formula becomes 1 over 15 sum of Cn times C of n minus 0, which is Cn. And therefore, this is multiplying by itself. And therefore, when you multiply all these pulses by themselves, you are going to find that the sum is going to become 15 divided by 15, and this becomes a 1. So the final resolution that we observe from here is as follows. The summary of what we have done is as follows: that the autocorrelation with 0 delay is equals to the autocorrelation with delay of n pulses or n symbols, and is equivalent to autocorrelation with 2 n symbols, like that, and this will always be equals to a 1. But when autocorrelation of 1 delay, or autocorrelation of delay of 2, autocorrelation of delay of 3, all these are going to be equal, and they're always going to be given by 1 over n. So having come with that agreement, then we come up with a solution that says that whenever we receive a PN sequence that meets this validation property, that means it's valid, it's random, and it's unpredictable. And the final diagram I would want to show here is that if you are to plot this autocorrelation function on dimension of n, you would observe that the autocorrelation functions, this is -1, this is +1, takes this shape. When at the value of n, it becomes, they are highly correlated. And at the value of 0, they are highly correlated. But whenever there is a delay of 1, 2, or 3 bits, they are completely uncorrelated. Anything with a correlation value of -1, that means that you cannot be able to predict it. So this is a very important property, that whenever you see that the autocorrelation function has a value of +1, it means that it's related to, the sequence is related to itself, but it's completely unrelated with any other subsequent sequence, and therefore you cannot be able to predict the sequence, this sequence, and with its delayed version of even if the delay is equals to 1. So that is the summary of the properties of the PN sequence.